Welcome to this presentation of Variational Learning is Effective for Large Deep Networks, which will be presented as a spotlight at ICML 2024. In this work, we show that, contrary to popular belief, variational learning can effectively be used to train large and deep neural networks by proposing an optimizer called IVON. Transformer LLMs up to the size of 773 million parameters that are trained with IVON show better validation perplexity at a similar compute budget when compared to models trained with AdamW. Similarly, we find when training ResNet 50 on ImageNet that models trained with IVON show lower validation error on the left, and on the right hand side shown is that they are better calibrated than models trained with AdamW. IVON achieves this by optimizing a variational objective that minimizes an expected loss over an approximate posterior, which in our case is a diagonal Gaussian distribution. IVON is similar to popular optimizers like RMS-Prop and Adam, but adds a sampling step of parameters from this approximate posterior to estimate the gradients of the expected loss. This gradient estimate is also reused with the reparameterization trick in order to estimate a Hessian. The Hessian is used to define the variance of the distribution, and the variance can also be adapted with an effective sample size lambda, which acts as an inverse temperature parameter. IVON is easy to implement in common deep learning packages. For example, in PyTorch, we release a pip installable package where IVON can simply replace any common optimizer, just like Adam, for example. However, one change is needed in order to sample parameters in order to estimate the gradients of the expected loss. Here we show further results in image classification tasks with different models, and we find that models trained with IVON, even at the learned mean, provide better downstream performance, but also better calibration and uncertainty than models trained with SGD or with AdamW. And when using the approximate posterior in order to sample models and average their predictions, here with 64 models, we find further improvements in terms of accuracy, calibration, and uncertainty. IVON's predictive uncertainty is also useful for OOD detection. On the left-hand side, we show that it clearly separates the in-domain data in red from the out-of-domain data shown in gray. On the right-hand side, we find that in terms of OOD detection metrics, IVON outperforms popular Bayesian deep learning methods such as MC dropout, Laplace, or SWAG. IVON also enables model adaptation through model merging without any extra cost. In model merging, parameters of trained neural networks are added or subtracted in order to add or remove knowledge to or from models. Improved model merging then requires Hessian approximations, which are approximated by IVON during training and come for free. And we find that this Hessian estimate improves over a squared gradient estimate of the diagonal fissure in terms of the downstream performance of the merged model, but also in terms of overhead, where IVON produces no overhead, but squared gradients need one further pass through the dataset. Finally, IVON also enables model understanding, for example by predicting test loss, by noting that the sensitivity of the model to data is proportional to a measure of prediction error and prediction variance, which is again computed by IVON for free. We use this to estimate a leave one out loss that estimates the test loss using only training data, and we find that IVON's estimate is faithful, while AdamW's estimate seems to diverge at later training stages. This sensitivity estimate can also be used to distinguish unusual data. For example, here shown on ImageNet, we find that low sensitivity examples are usual. For example, for the shark class, these are sharks shown in bright blue water, while the high sensitivity examples are unusual. For example, a shark stuck in the roof, a llama attached to a parachute, or teapots that don't follow the common shape of the low sensitivity examples. To conclude, among other challenges, such as uncertainty, variational learning can help to address two important problems of modern deep learning: model adaptation and model understanding. We propose a variational learning method called IVON, which effectively trains large and deep neural networks such as GPT-2 with a variational learning algorithm. IVON is pip installable, as shown here, and can easily be implemented for your project. Thank you for your attention.